Students, in our last class we have talked about free vibration of a taut string which is fixed at both ends, something like this. Okay, and we initially have derived natural frequencies and mode shapes for this string. We are going to go in slightly more details about that natural frequency and mode shapes in this particular class. Now I'll write down natural frequency and mode shapes equations in over here now for you. So the expression that we derived for natural frequency was something like this: n pi c by L. Okay, which essentially means that there are infinite number of natural frequencies as n ranges from 1 to infinity. So n can take any value of these integers, okay, which start from 1 and goes till infinity. So n can be anything between these infinite integers. It can take any value. Okay, so depending on which n value it is taking, that natural frequency we are considering. Okay, so for example, for first natural frequency n we are going to put as 1, and accordingly we are going to go further. Okay, so you will be able to appreciate that higher natural frequencies are integer multiples of the first natural frequency. Okay, so first natural frequency, that is omega n1, I'll be calling it that is equal to pi c by L. We know what is c is equal to square root of t by rho. Okay, so I'll be writing that, which is pi by L into t by rho. Okay, so this is what is first natural frequency, and all higher natural frequencies, that is omega n2, omega n3, okay, those are integer multiples of this first natural frequency. So you can write down omega n2 as 2 times omega n1, omega n3 as 3 times omega n3, and so on. And when you have such kind of conditions appearing, okay, so which happens in case of taut string, then let's say then if you pick or if you, let's say, disturb, if you pluck this particular string in certain fashion, then you can excite many such natural frequencies. Okay, so for initial condition, let's say you are disturbing this taut string, okay, by applying certain initial condition, you are plucking it over here. If you do so, then what will happen, a few natural modes will be excited. Okay, so first few natural modes, let's say, are excited, m number of natural modes are excited, and all those m number of natural modes are integer multiples of this fundamental natural frequency, which is omega n1. And when this thing happens, then whatever sound that is created by such kind of combination of m number of frequencies which are integer multiples of one frequency, then that sound is appreciated by human ear, and we find it very soothing, very nice to hear. And that is what actually the reason behind using such kind of strings in musical instruments. So you might have seen that there are so many musical instruments which are using strings to generate sound, and though that is actually the reason that I just now have told you, that when you disturb it with for certain initial conditions, then you kind of generate few natural modes of that string, and those few natural modes are integer multiples of the first fundamental frequency. Okay, and since these multiple frequencies which are created are integer multiples of each other, then that is something which is creating a very nice soothing sound, and our ear likes to hear it, and we feel it better, okay, when we hear such kind of sound. And you will also be able to appreciate that I'll write down this omega n once again over here. So that omega n is equal to n pi by L into t by rho. Okay, so this is what is omega n. So what we do is, let's say I'll consider first natural frequency 1 initially to start with. Okay, so let n be equal to 1. Okay, so let's say if you have a string instrument, okay, then what you do is one end of that string instrument is fixed. Okay, and what you do, you change that other fixed end, okay, by holding it at certain location, and depending on at what location you are holding it, that much amount of length will be selected. Okay, so if you hold it over here, then this much amount of length will be considered as length of that taut string, and accordingly for this length omega n1 will be generated. Okay, now if you want to change that frequency, okay, the frequency with which the string is vibrating, then what you have to do is you just have to shift where you are fixing this. Okay, so what you do is you move it either this side or over this side. Okay, if you move over this side, then this L will get reduced. Okay, and new L1 will come over here, and L1 will be smaller than L. So L1 is going to appear over here in the denominator, and natural frequency is going to increase. Okay, so first fundamental natural frequency of this string is same. Okay, rho has not changed at all. Okay, tension of the string also has not changed at all. We are keeping tension same, we are keeping rho same. Okay, rho is obviously the same because string is same, so rho is not going to change. So what you have changed is you have only changed the length of the string by holding it in some other position, and if you reduce the length of that string, then the natural frequency of that string increases. Okay, so for smaller strings, natural frequency is higher. Smaller strings offer higher stiffness, and hence natural frequencies are also higher in that case. Okay, when strings are longer, then natural frequencies are lesser, smaller. Okay, and you also know that we also have one more handle that we generally do with this adjustment of tension right in the beginning. Okay, so when you want to when you want to set your string instrument, then what you do initially is you adjust the tension and you set your string instrument, and after that is done, then you can move along this string instrument and you can pick any natural frequency that you want. And as this allows you infinite number of choices of natural frequency, because you can hold anywhere, right? Depending on where you are holding it, accordingly your natural frequency will be selected. So you have infinite number of choices of fundamental natural frequencies, and that is actually one very great advantage of the string instruments, and string instruments are therefore very popular in music domain. Okay, so this was about natural frequency, and we also have this is very brief about that. In the interest of time, we can only discuss this much. Okay, so we also have arrived at expression for the mode shape. So that expression of the mode shape was like this: sine n pi x by L. Okay, if you remember in multi-degree of freedom system, okay, so the system that we had started with, we initially obtained mode shapes 1 1 and 1 minus 1, if you remember. Okay, so for the kind of 2 degree of freedom system that we were considering. Okay, and then we converted these mode shapes to mass normalized mode shapes in such a way that let's say if this is u, okay, let me call this as u1 and u2, and we said that u1 transpose mass matrix times u1 should come out to be equal to 1. In order this thing to happen, we scaled this u1. Okay, similarly we also scaled u2, and we said that we have obtained mass normalized mode shapes. We also have seen it further that u2 transpose times m times u1 is equal to 0. Okay, and which we said that this is the statement of modal orthogonality of these mode shapes. Okay, so these mode shapes are orthogonal with each other with in consideration of this mass matrix. Okay, so similarly if you put k over here, still you will get this orthogonality condition satisfied. Okay. However, if you put k over here, then you are not going to get 1 as the answer, but you get omega n square as the answer, right? When you put k over here, right? For that particular mode shape which is mass normalized. This is something that we already have seen in case of multi-degree of freedom system. Now we are going to have a look at mode shape that we have derived for continuous system in light of whatever that we have derived for multi-degree of freedom system earlier. Okay, so initially let's try to see whether we can normalize this mode shape. Okay, whether we can find mass normalized mode shape. Okay, so this, let me call it as xn Okay, this is nth mode shape, and let me say that this nth mode shape, if I have to convert it to mass normalized one, then what I'll be doing is I'll be multiplying by this xn itself, and then we have mass term, which is nothing but rho, and xn itself. Once again, we'll be integrating it over entire domain from 0 to L. This is that integration is the additional thing which is coming into picture in this particular continuous system, because our this mass and stiffness is distributed. So mass is distributed, therefore you need to multiply by mode shape and integrate it from 0 to L. Then only you will be able to obtain that mass normalized mode shape. Okay, so I want this thing to be equal to 1. Therefore, I'll be scaling xn in such a way, so this xn will be scaled in such a way that this thing comes out to be equal to 1. So let me say that I am scaling it by multiplying by an. Okay, so if I do so, then I'll be putting this expression of xn over here, and what I'll get is this 0 to L an square into sine square n pi x over L times rho times dx. That needs to be equal to 1 in order that this equation is satisfied. In order that LHS is equal to 1, what should be an square? Okay, that is something that we are going to find out. That will give us value of an square, and so that we will be able to find out an, and we will be able to scale our mode shape such that it will come out to be equal to mass normalized one. Okay, so if we do so, then we'll have to integrate the sine square term, sine square n pi x by L. So what we can do is we'll be changing the sine square n pi x by L into 1 minus cosine of 2 n pi x by L, this entire stuff divided by 2 into rho dx. Okay, that needs to be equal to 1, and if you carry out this integration, then you will be able to appreciate that answer is obviously here an square is here, so an square times rho L by 2 is the answer of this LHS, and that needs to be equal to 1, which essentially tells you that an should be equal to square root of 2 over rho L. Therefore, your mass normalized mode shape will be square root of 2 over rho L into sine of n pi x over L. This is what is the expression of mass normalized mode shape, right? So let me show you how exactly these mode shapes will look like. Okay, so in our earlier case, when we were considering multi-degree of freedom system, the kind of mode shape that we obtained were like this, right? 1 1 and 1 minus 1. So what they were looking like, so let's say that we were having mass particle number 1 over here and mass particle number 2 over here, and then there was this spring 1 and spring 2. Okay, so or maybe this, that should be a better way. Okay, so this is the spring, okay, and this is x1, this is x2. Okay, now if you decide to plot x1 again, x1 and x2, then when x1 is 1, x2 is also 1. Okay, so this is what is the mode shape that is going to look like, mode shape number 1. In the other case, x1 is 1 and x2 is minus 1, and this is what is the mode shape that you have obtained in the other case, right? This was for multi-degree of freedom system, which we have considered earlier. Now for this system, which is this continuous system, we have obtained mode shape like this, okay, where we have rather infinite mode shapes, 2 over rho L square root of this quantity multiplied by sine n pi x over L. Okay, so let's consider the first mode shape. So in order to do that, we'll be putting n value as 1, and what we are going to get is this sine of pi x over L. Okay, so if you decide to plot this, it will look something like this. Okay, this is the first mode shape. Okay, if you decide to plot the second mode shape, which will be the square root of 2 over rho L times sine of 2 pi x over L, then it would look like this. And third mode shape will be like this. So you will be able to appreciate that these mode shapes are satisfying your boundary conditions, right? All these mode shapes are satisfying boundary conditions individually. Okay, and this is what is the shape. So as time is going to change, so only multiplier to this is going to change. So it is going to change into such kind of new shape, which will be the same shape but multiplied by a constant value. Okay, that constant value can be 0 at times, or it can be some other scalar value, right? And accordingly the string will vibrate from this stage to multiple other stages. Okay, similarly over here. Okay, so that this shape is going to remain constant, owing only that multiplier is going to change. Okay, so even this is the same shape, okay, multiplied by -1. So this is that shape, right? This point which remains fixed is called as node. Okay, so you have one node at this end and another node at this end, which are nothing but actually the boundary conditions, and because of that you get to see node over here. However, there is no any node for first mode shape in between the domain. Okay, so this is the domain of the string, and there is no any node for first mode shape. For second mode shape you get to see one node inside. For third mode shape you get to see two nodes inside, and so on. So you have infinite number of such mode shapes. Okay, so this is what is a brief about mode shapes and natural frequencies. Now whatever that we have discussed so far can be extended further to study force vibrations, and however I am not going to go into very great details of it, but I'll be showing you how we can set up that formalism. And in order to do that, we'll be first of all invoking that idea which we actually have talked about in our last class, that the displacement is written as superposition of all mode shapes. Okay, so what we have written in yesterday's class, that is actually that modal superposition theorem or modal expansion theorem, in which we have written y as summation of xn times tn, where n was changing from 1 to infinity. Okay, so this tn is function of time, xn is function of x, and we know what is the expression of xn. Xn's expression is 2 over square root of rho L times sine n pi x over L, and tn is harmonic in nature with natural frequency omega n, right? So tn expression of that is an cosine omega n t plus bn sine omega n t. Okay, so depending on what n is, that natural frequency will be selected. So tn is harmonic in time, and xn is what is this mode shape that you have obtained. For this particular case, which is a taut string and fixed at both ends, you get to see sine as the sine function as the mode shape. However, you need not get sine, you can get any other function. Okay, so it can be a very different function. You right now I are not aware of that. You cannot say that it will be essentially the harmonic function. Okay, it need not be harmonic. It all depends on what kind of boundary conditions are posed, and you can try it out for other boundary conditions, and you will be able to see that that doesn't always come out to be harmonic function. Okay. Now this modal expansion theorem that I have now stated over here, that is used in obtaining the solution of force vibrations. The way we have done in case of multi-degree of freedom system. Okay, so this is nothing but kind of a multi-degree of freedom system, but we have infinite number of degrees of freedom, and that's why we are ending up into all that integration business. Otherwise, we in multi-degree of freedom system that we were considering, we were not actually encountering any such integrations over there. Okay, we were operating on matrix equations at that time, but here we have integral equations to take care of. Okay, okay, so let's try to see how we can use this modal expansion theorem in order to arrive at a solution for force vibration. I'm not going to solve any problem as such, but I'm going to show you that formalism so that it will be clear to you and you will be able to use it if required. Okay, so let me write down that expression of equation of motion, which is like t del square y by del x square equal to rho del square y by del t square. This much we have written for free vibration analysis. However, when we have any force coming on to this, then we'll be taking care of that force over here. Okay, so you will be applying certain force. That force again will be function of x. You need to appreciate that the force is also a distributed force, distributed along x, and it will also vary on time domain. So this force is varying along x, it is also varying along time, right? So in this, what you will be doing is you will be exploiting this modal expansion theorem and putting value of y by using this modal expansion theorem. Okay, and by that way what we'll get is this. Okay, so t times summation of this xn tn. So this t is different and this t is different. This is tension and this t is, so let me mark this t by t bar so that you will be able to appreciate that this t is different. Okay, this is what is y expression which I am putting over here. However, I need to take second derivative of this y with respect to x. This is obviously not function of x, so we will not be differentiating this, but we will have to differentiate this. Okay, I am marking these two lines over here which are representing that this is second order space derivative. Okay, it is like this, d square xn by dx square. Okay, this is shorthand notation of that. So I'm using that notation over here, and n is ranging from 1 to infinity. That is equal to rho times summation of this quantity. Now this y, if you see what is there in this equation, you have del square y by del t square. So you have partial derivative of y with respect to time. Now obviously xn will not be differentiated, and what is going to be differentiated is this t, and that will be differentiated with time. And in order to show that it is second derivative of time, I am putting these two dots. This is what is the convention that we generally follow. Okay, so when you have space derivatives, then you put these lines, and when you have time derivatives, then you put these dots. Okay, so this is nothing but d square tn by dt square. Okay, so this is how it is appearing, plus f, it should be plus, I made mistake there, so it's plus f of x and t. Okay, now what we do over here is that we multiply by some mth x. Okay, some that is some let's say fourth mode shape. Okay, where m is equal to 4. Okay, so if I, let's say, multiply by fourth mode shape to this entire equation, and this is just for example, it need not be 4. We actually go from right from 1 to infinity. Okay, and I'm just taking one example and trying to show you. That's why I said that let's say it is fourth one. Okay, and if you do so, and if you multiply, let's say it is fourth one, and I'll be multiplying, and again I'll be integrating. Okay, if I do so, then what I'll get is 0 to L, then I have this t bar, Before that t bar I'll be writing x4, and then I have this t bar coming over here. Then I have the summation n ranging from 1 to infinity xn tn, and this entire thing needs to be integrated with respect to dx. So dx is there, then that needs to be equal to 0 to L. Again x4 I am multiplying by, then you have rho, and then you have this summation term. I have second derivative of it. Okay, t double dot of n dx plus integration from 0 to L x4 f of xt dt. Okay, now I'll slightly simplify it and I'll write it in this way. Okay, you need to appreciate that you are integrating it with respect to x. Okay, and this tn has nothing to do with x, so it can come out of the integration. Similarly over here, this can also come out of the integration. Okay, however, I am not taking this t bar and rho out of the integration, because the kind of string that we are talking about, that is a very specific case where rho and t, they are not changing with x. But you can have a condition where rho and t can change with x. Okay, obviously in that case expression of this mode shape will be different, and if you have seen that I am not putting expression of mode shape anywhere over here, I am writing it in the most generalized sense. Okay, so therefore in order to respect that generalization, I am keeping this t bar and rho inside the integration. Okay, and I'll be writing it this way: integration from 0 to L x4 t bar, and then summation this tn is going to come out. And then you have rho over here, then xn's here, and actually summation, yeah, it won't be written this way. Summation sign also needs to be respected, so we'll be writing it in this way. So we'll be putting summation sign outside. Okay, so if I put that summation sign outside, summation n ranging from 1 to infinity, integration from 0 to L x4 t bar into xn dx. Inside this summation itself, I have this tn term. This needs to be equal to integration from n to infinity. Then I have this term. Here you have second derivative of this x. Here you are having x4 t bar xn dx times second derivative of tn, and then this big bracket which is inside this summation term, that gets completed. That is equal to integration from 0 to L x4 f of xt dx. Okay, now if we look over here, here we have a rho. Unfortunately I made one more mistake here, it should be rho here. Okay, so if you look at this, okay, you know that when n is equal to 4, then you get this term x4 rho x4 dx. Okay, and just now we have said that these x's are mass normalized ones, so this needs to be equal to 1. And also modal orthogonality holds which essentially means that when n is anything other than 4, when n is not equal to 4, then in that case this integration, for n not equal to 4, this integration will go to 0. When n equal to 1, this integration will have value equal to 1, and for any other case this integration will have value equal to 0. Similarly, it can also be proven that this integration, okay, so which is this this one, 0 to L, we are having x4 here, then you have t bar, and you are having xn's second derivative dx. Okay, it can be proven that for when n is equal to, when n is not equal to 4, rather when n is not equal to 4, then this term comes out to be equal to 0, and when n is equal to 4, then this term comes out to be equal to minus omega n square. Okay, you will be able to prove it for the particular case that we are considering. What you have to do is you'll just plug in the values and you will be able to show it that this is what is the result. Okay, so finally if you see for all other values you are getting 0, right? So now I'll replace this 4 by m. Okay, it can be any mth mode, right? It can happen for any mth mode. So I'll replace this 4 by m, and I'll use whatever that we just have now talked about, and I'll be plugging all these things in this equation, and then I'll be able to write it down in this way. This comes out to be, I guess I was right earlier, there has to be minus sign over here. Okay, so there has to be minus sign over here. Okay, and if I do so, then I'll be able to write it in this fashion. Minus omega m square times tm, that comes out to be equal to tm double dot minus, I'll be calling it as f tilde, which I'll be writing as tm double dot plus omega m square tm is equal to f tilde. This is one value, okay, which is coming because of integration 0 to L xm f of xt dx. Okay, so whatever comes out, this answer of this integration is what is f tilde. Okay, this is a scalar, and these are infinite number of single degree of freedom systems. Okay, and similar stuff we have derived in case of multi degree of freedom system as well. Over there we have obtained m number of, so depending on how many number of degrees of freedom, we have obtained those many number of equations which were ordinary differential equations, and we said that those are almost like single degree of freedom system. So in the similar fashion we are again obtaining ordinary differential equations in terms of this tm. Okay, and we'll be solving that tm for that particular f tilde, and that is what is actually the story of force vibration of this continuous system. So from the perspective of this course, in the light of the very limited time that we have and the pandemic situation which is forcing us to go in a very different mode of teaching this time, so in that in light of all that, we'll be stopping over here for this particular course. However, there are still so many things to learn in this, and you can always explore it, and you are always welcome to do that. Okay, if you feel that you need to have a word with me regarding whatever that we have covered, whatever that we have not covered, then you are always welcome. Okay, thank you so much, and wish you very best of luck for your exam whenever it is going to happen. I don't know when it is going to happen. I'm going to post one quiz for you very soon on Moodle, So please stay updated and solve that quiz, and wish you very best of luck for all your future endeavors. Okay, bye. Thank